The space between stars is not simply nothing. It is a near-perfect vacuum, flooded with cosmic radiation, threaded with invisible magnetic fields, and stretched across distances so vast that our fastest spacecraft would need over 70,000 years to cross just the gap to the nearest neighbouring star. What fills that emptiness is far more terrifying than the emptiness itself. If you enjoy deep dives that change the way you see the universe, take a moment to hit that like button and subscribe. It genuinely helps more than you might think, and it keeps these stories coming. Now, settle in and get yourself comfortable. Let's begin. Look up at the night sky on a clear evening, far from the glow of city lights, and you will see something breathtaking. Thousands of stars scattered across the darkness, a dense, glowing band of light cutting across the sky from horizon to horizon. Clusters and smudges of brightness are packed so tightly together that they seem to blur into one another. The sky looks full. It looks crowded. It looks like the universe is bursting with matter, light, and energy crammed into every available corner of the cosmos. This impression is one of the greatest optical illusions in nature. Those stars that appear to sit side by side in the sky are not neighbours. They are separated by distances so extreme that light itself, the fastest thing in the universe, needs years to travel between them. The two stars that form a close visual pair in your favourite constellation might actually be hundreds of light years apart in three-dimensional space, one vastly closer to you and the other unimaginably farther away, with no physical connection between them whatsoever. The night sky flattens the universe into a dome. It compresses trillions of miles of depth into what looks like a painted ceiling. And because of that compression, we walk through our lives believing that space is a place filled with stars. It is not. Space is a place filled with space. The overwhelming majority of the volume of our galaxy contains no stars, no planets, no moons, no asteroids, no comets. Between one star and the next lies a region so devoid of anything recognizable that it challenges the human brain to even imagine it. If you could somehow stand in the middle of the gap between our Sun and its nearest stellar neighbour, Proxima Centauri, and look around in every direction, you would see nothing. Not darkness, the way you experience it in a room with the lights off. Darkness on a scale that has no edges, no walls, no floor. A blackness so complete and so vast that it extends for trillions of miles in every direction before the next point of light appears. There is no sound, there is no wind, there is no warmth, and there is almost no matter. Almost. This is where most people stop thinking about it. They file interstellar space under the category of nothing and move on. And this is exactly where the real story begins. Because the space between stars is not nothing, it is something. It has structure, it has composition, it has behaviour. And understanding what it actually is, what fills those incomprehensible gaps between the stars, reveals a truth about the galaxy that most people never encounter. Scientists call it the interstellar medium. The name sounds clinical, almost boring, like a technical footnote buried in an astrophysics paper. But the interstellar medium is one of the most important environments in the entire Milky Way. It is the material that fills the space between the stars, and it is not empty vacuum. It is an incredibly thin, incredibly vast sea of gas, dust, charged particles, magnetic fields, and high-energy radiation that stretches across the full width of the galaxy. Every cubic centimetre of the space between stars contains some trace of this material. It is everywhere. It is always there. And it plays a role in nearly every major process the galaxy performs, from the birth of new stars to the death of old ones. Here is what the interstellar medium is made of. By mass, Approximately 99% of it is gas. The remaining 1% is dust. That ratio alone tells you something important. When scientists talk about what exists between the stars, they are overwhelmingly talking about gas, not thick, breathable gas like the atmosphere you are sitting in right now. Gas so thin, so diffuse, so spread out across such enormous volumes that it makes the best laboratory vacuum on Earth look like a thick soup by comparison. But it is gas nonetheless, and it has a composition that traces directly back to the earliest moments of the universe. Roughly 70% of the interstellar gas by mass is hydrogen. This is the simplest element in existence: one proton, one electron. It is also the most abundant element in the universe, a direct product of the Big Bang itself. Nearly all the hydrogen that exists between the stars today was created in the first few minutes after the universe began, when temperatures were high enough for protons to form, but the universe was expanding too quickly for most of them to fuse into heavier elements. That primordial hydrogen has been drifting through galaxies ever since, collecting in some regions, dispersing in others, occasionally collapsing under gravity to form new stars, and then being recycled back into interstellar space when those stars die. The next most abundant component is helium, making up roughly 28% of the interstellar gas by mass. Helium was also produced during Big Bang nucleosynthesis, in the first minutes of cosmic time. Together, hydrogen and helium account for nearly all the gas in the interstellar medium. Everything else, carbon, oxygen, nitrogen, iron, silicon, every element heavier than helium that exists between the stars adds up to less than 2% of the total mass. Astronomers sometimes refer to all these heavier elements collectively as metals, which is a source of endless confusion for anyone who studied chemistry, because in this context, oxygen counts as a metal, and so does carbon. The convention is a quirk of astronomical history, but the point it conveys is accurate. The space between stars is dominated almost entirely by the two lightest elements in the periodic table. Everything else is a trace. That remaining 1% of the interstellar medium, the dust, is something entirely different. Interstellar dust is not like the dust that accumulates on your bookshelves. It is composed of tiny solid particles, typically less than a micrometer across, made of silicates, carbon compounds, and in some cases, coatings of water ice, carbon monoxide ice, ammonia ice. These grains are incredibly small, roughly comparable to the wavelength of visible light, which is precisely why they are so effective at blocking and scattering starlight. When you see a dark lane running through a photograph of the Milky Way, you are looking at interstellar dust clouds so thick that they absorb the light from billions of stars behind them. The dust does not just passively sit there, it absorbs light at shorter wavelengths, particularly blue light, and re-emits that energy as infrared radiation. This process, called interstellar reddening, makes distant stars appear redder and dimmer than they truly are. For centuries, it fooled astronomers into underestimating the size of the galaxy and the distances to faraway objects, but describing the interstellar medium as simply gas and dust gives a misleading impression of uniformity. The interstellar medium is not a smooth, evenly distributed fog. It is one of the most wildly variable environments in the galaxy. Different regions of the space between stars exist in dramatically different physical states, and scientists have identified several distinct phases that coexist and interact across the galaxy. The first is the cold neutral medium. This is gas that has cooled to temperatures around 50 to 100 Kelvin, which is roughly negative 200 degrees Celsius. At these temperatures, hydrogen exists primarily in its neutral atomic form, meaning the electrons are bound to the protons and the gas carries no net electrical charge. The cold neutral medium tends to concentrate in relatively dense clumps and clouds, and it makes up a significant fraction of the total mass of the interstellar medium, despite occupying only a small fraction of the total volume. These clouds of cold neutral hydrogen are the raw material from which molecular clouds can form, and molecular clouds are the places where new stars are born. Then there is the warm neutral medium. This is hydrogen gas at temperatures around 6,000 to 10,000 Kelvin. It is still electrically neutral, atoms with their electrons intact, but it is far warmer and far more diffuse than the cold phase. The warm neutral medium fills a much larger fraction of the galaxy's volume, spreading out between the denser cold clouds like an ocean between islands. It represents one of the most common states of interstellar gas by volume. Next comes the warm ionized medium. At similar temperatures to the warm neutral medium, around 8,000 Kelvin, this phase differs in one critical respect. The hydrogen is ionized. The electrons have been stripped from the atoms, primarily by ultraviolet radiation from hot, massive stars. The warm ionized medium fills an enormous volume of the galaxy, particularly in regions near stellar nurseries and in the galactic halo above and below the plane of the disk. It was largely invisible to early astronomers because ionized hydrogen at these temperatures does not produce the same strong radio signatures as neutral hydrogen. Its detection required specialized observations of faint emission lines, particularly a spectral line called hydrogen alpha. The warm ionized medium was a relatively late addition to our understanding of interstellar structure, and its full extent is still being mapped. Finally, there is the hot ionized medium. This is the most extreme phase of the interstellar gas. Heated to temperatures exceeding 1 million Kelvin by the shock waves from supernova explosions, this phase consists of extremely diffuse, fully ionized plasma. The density is astonishingly low, as little as 1/10,000th of an atom per cubic centimeter, but its temperatures are extraordinary. Supernovae are the primary engines that create this phase. When a massive star reaches the end of its life and detonates, the blast wave expands outward at thousands of kilometers per second, sweeping up, heating, and ionizing the surrounding interstellar gas. These expanding bubbles of superheated plasma can persist for millions of years and can grow to hundreds of light years in diameter. The hot ionized medium is thought to fill a large fraction of the galactic volume, perhaps as much as 50% in some models, creating a pervasive network of overlapping bubbles and tunnels of million-degree gas threading through the cooler phases. These four phases do not exist in isolation. They are in constant interaction. Cold clouds are embedded within warmer gas. Supernova shock waves crash into dense molecular regions, sometimes compressing them enough to trigger gravitational collapse and new star formation, and sometimes blasting them apart and dispersing their material into the surrounding volume. The interstellar medium is a dynamic, turbulent, constantly churning system. Material cycles between phases over millions of years. Gas cools, condenses, forms stars, gets heated and dispersed by those stars, cools again, and the cycle continues. The galaxy is not a static painting. It is a living system, and the interstellar medium is the circulatory system that drives it. Our own solar system sits inside one of these dynamic features. It is called the local bubble, and it is a region of the hot, ionized medium that extends roughly 1,000 light-years across. The local bubble was likely carved out by a series of supernova explosions that occurred between 10 and 20 million years ago. Those explosions swept away the denser interstellar gas that had previously occupied this region, leaving behind a cavity of extremely low-density, high-temperature plasma. We live inside this cavity. When you look at the night sky, you are peering out through the walls of a bubble blown by dead stars. Immediately surrounding the solar system within this larger bubble is a smaller structure called the local interstellar cloud, sometimes referred to as the local fluff. This is a relatively warm, partially ionized cloud of gas with a density of roughly 0.3 atoms per cubic centimeter, slightly denser than the surrounding bubble but still extraordinarily rarefied by any terrestrial standard. The Sun is currently passing through this cloud, and it is the interstellar material that Voyager 1 and Voyager 2 first encountered when they crossed beyond the heliosphere, the bubble of solar wind that surrounds our solar system. The local interstellar cloud has a temperature of approximately 6,000 to 7,000 Kelvin and is flowing through our neighborhood of the galaxy at roughly 26 kilometers per second. In a few thousand years, the solar system will leave this cloud and enter a different region of interstellar space, possibly one that is denser or more tenuous. The environment between the stars is not static, even in our own tiny corner of the galaxy. There is one more component of the interstellar medium that most people never hear about, but that pervades the entire space between stars: magnetic fields. The galaxy is threaded with magnetic fields that extend across thousands of light years, typically measuring a few microgauss in strength. A microgauss is an almost inconceivably weak unit of magnetic force. The refrigerator magnet on your kitchen door is roughly 10 million times stronger than the interstellar magnetic field. But what the interstellar field lacks in intensity, it compensates for in scale. These magnetic fields stretch across the entire galactic disk and into the halo, influencing the motion of charged particles, shaping the structure of the interstellar gas, and playing a critical role in how cosmic rays propagate through the galaxy. Without interstellar magnetic fields, the behavior of the medium would be fundamentally different, and the galaxy would look nothing like it does today. Cosmic rays themselves are another omnipresent component of the interstellar environment. These are not rays in the traditional sense. They are particles, primarily protons but also heavier atomic nuclei, that have been accelerated to extraordinary energies by violent astrophysical events, particularly supernova remnant shockwaves. Some cosmic ray particles travel at 99.9% of the speed of light. They carry individual particle energies that can exceed anything produced by the most powerful human-built particle accelerators on Earth. These particles zip through the interstellar medium constantly, deflected and scattered by the magnetic fields, interacting with the gas and dust, and penetrating deep into any structure they encounter. They are a permanent feature of the space between stars, an invisible rain of high-energy particles that fills the galaxy from edge to edge. So let us take stock of what actually exists in the space between stars. It is not nothing. It is a sea of gas, primarily hydrogen and helium, arranged in multiple coexisting phases at vastly different temperatures and densities. It contains tiny but astrophysically important grains of dust that absorb and scatter light, reshaping what we can see. It is permeated by magnetic fields that extend across thousands of light years and influence the motion of charged particles. It is saturated with cosmic rays, high-energy particles that travel at nearly the speed of light and carry enormous individual energies. And it is dynamic, shaped by the explosions of dying stars, the radiation of living ones, and the gravitational interactions of the galaxy itself. This is the environment that lies between every star you have ever seen. Not vacuum, not void, not nothing. A structured, complex, physically real medium that scientists have spent decades studying and still do not fully understand. Every phase transition, every interaction between shockwaves and cold clouds, every magnetic field line threading through the galactic disk represents a piece of an ongoing puzzle that connects the largest scales of galactic evolution to the smallest scales of atomic and molecular physics. And here is the crucial detail that most people miss entirely. The interstellar medium is not just a backdrop, it is a participant. Without it, no new stars could form. Stars are born when regions of the interstellar medium specifically the cold, dense molecular clouds, collapse under their own gravity. If the interstellar medium did not exist, star formation would have ended billions of years ago when the first generation of stars consumed the available material. The galaxy would be a graveyard of dead stellar remnants with no new light to replace them. Instead, the interstellar medium acts as a reservoir. Stars form from it, live their lives, and then return their material back into it through stellar winds, planetary nebulae, and supernova explosions, often enriched with heavier elements forged in their cores. The next generation of stars forms from this enriched material, incorporating those heavier elements into planets, moons, and ultimately the chemistry of life. Every atom of carbon in your body, every atom of oxygen you breathe, was manufactured inside a star, ejected into the interstellar medium, drifted through the space between stars for millions of years, and then was swept up into the collapsing cloud that formed our solar system. The interstellar medium is the bridge between stellar generations. It is the mechanism by which the galaxy renews itself. Understanding this changes everything about how we should think about the space between stars. It is not an absence, it is a presence. A thin, vast, structured, and essential presence that defines the character of the galaxy. But there is a trap in this understanding, and it is easy to fall into. Learning that the interstellar medium is not empty can create the impression that it is therefore substantial, that it is filled with useful material, that there is something out there to work with. There is not, because for all its scientific importance, for all its role in galactic evolution, the interstellar medium is staggeringly, almost incomprehensibly thin. The fact that it contains something does not mean it contains enough of anything to matter on any human scale. The gas densities we have been discussing, 1 atom per cubic centimeter in typical regions, a fraction of an atom per cubic centimeter in the hot phase, are so low that they represent conditions more extreme than any vacuum humans have ever created in a laboratory. The interstellar medium exists. It is real. It is measurable. And it is, for all practical purposes, as close to nothing as the universe can get while still technically being something. This tension between the interstellar medium being scientifically significant and practically negligible is the heart of the story. And it is a tension that only sharpens as we move deeper into the true scale of what lies between the stars. Because the emptiness of the interstellar medium is not just an abstract physical fact, it is a barrier. And the distances across which that emptiness stretches are far larger and far more terrifying than most people have ever been told. Let us begin with a single cubic centimeter. Hold your thumb and forefinger about a centimeter apart. That tiny gap, roughly the width of a pencil eraser, defines a volume of space so small you could fit hundreds of them inside a teaspoon. Now consider what that volume contains, depending on where in the universe it happens to be. At sea level on Earth, that cubic centimeter of air holds approximately 2.5 times 10 to the 19th power molecules. That is 25 quintillion. Written out, it is a 2 followed by a 5 followed by 18 zeros. Every cubic centimeter of every breath you take contains that many molecules of nitrogen, oxygen, argon, and trace gases, all bouncing off one another billions of times per second, creating the pressure and temperature you feel as the ordinary atmosphere of a pleasant afternoon. Now move that cubic centimeter into the best vacuum chamber ever built by human engineers. The most advanced ultra-high vacuum systems in research laboratories can pump a chamber down to a few thousand molecules per cubic centimeter. That is a reduction by a factor of more than 10 quadrillion compared to sea level air. At those densities, individual molecules travel for kilometers between collisions. These are the conditions required for manufacturing semiconductors, studying surface physics, and simulating aspects of the space environment for satellite testing. They represent the most extreme emptiness that human technology can reliably produce. Now move that cubic centimeter into the space between stars. In a typical region of the interstellar medium, that same cubic centimeter contains approximately one atom. One. Not 100. Not 1,000. One single hydrogen atom drifting in a volume that, on Earth, would hold 25 quintillion molecules. In the hot, ionized phase of the interstellar medium, the number drops further. It can fall to one atom per every 10,000 cubic centimeters. Imagine a volume the size of a large moving box, the kind you would use to pack dishes when changing apartments, and place inside it a single hydrogen atom. That is the density of the hottest, most diffuse phase of the gas that fills the space between the stars. These numbers are worth pausing over because they destroy a common misconception. When people learn that interstellar space is not truly empty and that it contains gas and dust, there is a natural tendency to picture something like a very thin fog, a haze, a faint mist that you might be able to detect if you squinted hard enough. That image is wrong by a margin so vast it barely qualifies as the same category of physical experience. The interstellar medium is not a thin fog. It is a vacuum so extreme that it makes the most advanced vacuum chambers on Earth look positively dense. The fact that it contains anything at all is detectable only because the volumes involved are so enormous that even one atom per cubic centimeter, accumulated across trillions upon trillions of cubic centimeters, adds up to a measurable quantity of matter. On any human scale, on any scale that your body or your senses or your engineering could interact with, the interstellar medium is indistinguishable from perfect emptiness. Here is another way to grasp this. Take all the interstellar gas contained within 1 cubic light-year of space. A cubic light-year is an enormous volume, roughly 9.5 trillion kilometers on each side. That is a box so large that light itself would need a year to cross it. Now, take every atom of gas inside that volume and compress it down into a solid sphere at the density of water. The resulting sphere would be remarkably small. Despite starting with a volume that dwarfs the entire solar system, you would end up with a ball roughly the size of a single planet. All the matter in a cubic light-year of interstellar space, squeezed together, would fit inside something no larger than Jupiter. One planet's worth of material spread across a volume that light takes a year to cross. The rest of that cubic light-year, the overwhelming, crushing majority of it, is void. This is the reality that the night sky hides from you. The galaxy is not made of stars. The galaxy is made of emptiness, with stars sprinkled through it at intervals so vast that the emptiness is the dominant feature by every conceivable measure. Stars are exceptions. The interstellar void is the rule. And the void between any two neighboring stars is not a small gap to be hopped across. It is an abyss. Consider the distance to the nearest star system. Proxima Centauri, the closest known star to our Sun, sits approximately 4.24 light-years away. That translates to roughly 40 trillion kilometers, 40 followed by 12 zeros. This is the shortest stellar distance in our entire neighborhood of the galaxy, the absolute minimum gap between our Sun and any other star, and yet it is so large that human-built machines, traveling at the fastest speeds we have ever achieved, would require tens of thousands of years to cross it. To develop some intuition for what 40 trillion kilometers actually means, consider the following. The Earth orbits the Sun at a distance of about 150 million kilometers, a unit astronomers call 1 astronomical unit. Proxima Centauri is approximately 268,000 astronomical units away. If you could somehow drive a car at highway speed, roughly 100 kilometers per hour, without ever stopping for fuel or rest, you would reach the Sun in about 170 years. To reach Proxima Centauri at that same speed, you would need more than 45 million years. The dinosaurs would still be walking the Earth when you started the trip. They would have gone extinct, mammals would have risen, primates would have evolved, human civilization would have been born and possibly ended, all before you arrived. And this is the closest star. The average distance between neighboring stars in our region of the galaxy is larger, typically around 5 light-years, but varying considerably depending on location within the galactic disk. Toward the center of the Milky Way, stars pack more closely together, though closely still means trillions of kilometers. In the outer reaches of the galactic disk and in the halo above and below the plane, stars are spaced even farther apart. In every case, the gaps between them are filled with the same astonishingly tenuous interstellar medium we have been describing. Trillions of kilometers of near vacuum, atom by sparse atom, stretching between each island of light. This is not an academic observation. It has been directly confirmed by the only human-made objects that have ever reached interstellar space. Voyager 1, launched from Earth on September 5, 1977. Its primary mission was to study Jupiter and Saturn, which it did with spectacular success. But after those encounters, it kept going. Powered by the radioactive decay of plutonium in its 3 radioisotope thermoelectric generators, Voyager 1 continued outward from the Sun at roughly 17 kilometers per second, or about 61,000 kilometers per hour. Year after year, decade after decade, it flew. It passed the orbit of Pluto. It entered the outermost regions of the heliosphere, the bubble of charged particles and magnetic fields that the Sun inflates around itself. And on August 25, 2012, something changed. Voyager 1's instruments detected a dramatic shift in its environment. The density of charged particles around the spacecraft increased sharply. The intensity of galactic cosmic rays, high-energy particles originating from outside the solar system, jumped upward. The plasma environment transformed from one dominated by the outward-flowing solar wind to one dominated by the denser, colder plasma of the interstellar medium. After 35 years of flight and a distance of over 121 astronomical units from the Sun, Voyager 1 had crossed the heliopause, the boundary where the Sun's influence gives way to the interstellar environment, and entered the space between the stars. But this description, crossed the heliopause and entered interstellar space, makes the transition sound far cleaner than it actually was. Voyager 1 did not pass through a single doorway from the solar system into the void. It crossed a series of boundaries, each one marking a distinct physical transition, and the crossing took years, not moments. Understanding these layers matters, because they reveal just how structured the border between solar space and interstellar space truly is, and how much protection we lose when we leave. The first boundary Voyager 1 encountered was the termination shock. The Sun continuously blows a wind of charged particles outward in every direction, at speeds ranging from 400 to 800 kilometers per second. This solar wind inflates the heliosphere, pushing against the pressure of the interstellar medium, but the interstellar medium pushes back. At a certain distance from the Sun, the outward pressure of the solar wind can no longer sustain its supersonic speed against the inward pressure of the interstellar gas. The wind abruptly decelerates from supersonic to subsonic velocities, and this deceleration creates a shock wave, a standing wave in the plasma that marks the beginning of the heliosphere's outer structure. Voyager 1 crossed the termination shock in December 2004 at a distance of roughly 94 astronomical units from the Sun. Voyager 2 crossed it in August 2007 at approximately 84 astronomical units, a difference that revealed the heliosphere is not a perfect sphere, but an asymmetric structure compressed on one side by the interstellar medium's own motion relative to the Sun. Beyond the termination shock lies the heliosheath. This is a thick, turbulent region where the decelerated solar wind piles up against the surrounding interstellar medium, creating a zone of compressed, heated, chaotic plasma. The heliosheath is not calm. It is a roiling boundary layer where solar and interstellar materials interact, mix, and struggle for dominance. Magnetic fields tangle. Particle populations from both sides intermingle. Voyager 1 spent 8 years traversing the heliosheath before finally reaching the heliopause itself in 2012. 8 years of continuous travel at 17 kilometers per second, covering roughly 4 billion kilometers, just across the boundary layer between solar space and interstellar space. That single transition zone, a region most people have never heard of, is comparable to the distance from the Sun to Neptune. The heliopause is the outermost boundary, the surface where the pressure of the solar wind finally balances the pressure of the interstellar medium, and the Sun's direct influence effectively ends. This is what Voyager 1 crossed in August 2012, and Voyager 2 crossed in November 2018. Beyond it, the interstellar medium begins in earnest. But even here, the transition was not perfectly sharp. Both Voyagers detected a complex layered structure at the heliopause, with magnetic field directions shifting, particle populations fluctuating, and plasma densities changing over distances of millions of kilometers. The edge of the heliosphere is not a wall. It is a membrane, thick and textured, and crossing it is a process that unfolds over months of spacecraft travel. This layered complexity matters for a simple reason. Every layer Voyager crossed on its way out, the termination shock, the heliosheath, the heliopause, represents a component of a structure that the Sun has built around itself using nothing more than the outward pressure of its own wind. That structure took Voyager 8 years to traverse. It is not a line on a map. It is a physically thick, turbulent, multi-layered boundary between two fundamentally different environments. And once a traveler passes through all of it and emerges on the other side, there is no equivalent structure ahead for light years. The medium that awaits on the far side has been waiting for billions of years. There is one more feature of the space between the heliosphere and the nearest star that deserves attention, because it is often misunderstood as offering something it does not. The Oort cloud is a hypothesized shell of icy bodies, comets, and frozen debris left over from the formation of the solar system that is thought to extend from roughly 2,000 astronomical units out to perhaps 100,000 astronomical units from the Sun, or roughly 1.5 light years. If this shell exists as current models predict, it means the solar system's gravitational influence extends far beyond the heliosphere, reaching almost halfway to Proxima Centauri in terms of the Sun's ability to loosely hold objects in distant, fragile orbits. At first glance, this might seem encouraging. Perhaps the Oort cloud offers waypoints, resource depots, or at least landmarks along the journey to the nearest star. It does not. The Oort cloud, if it exists, is estimated to contain several Earth masses of material spread across a shell trillions of kilometers thick. The average distance between individual Oort cloud objects is estimated to be tens of millions of kilometers. You could fly through the Oort cloud for centuries and never come within visual range of a single body. The objects themselves are small, cold, and dark, frozen chunks of ice and rock drifting in orbits so distant that the Sun appears as little more than a bright star. They offer no fuel, no shelter, and no navigational utility. They are ghosts at the edge of the Sun's gravitational reach, so sparse and so scattered that they reinforce the emptiness rather than relieving it. The Oort cloud is not a resource. It is a reminder that even the solar system's most extended structure is pitifully thin compared to the gulf that separates us from the stars. Beyond the outer edge of the Oort cloud, even the Sun's tenuous gravitational claim fades. From there to the corresponding outer reaches of Proxima Centauri's own gravitational domain, there is truly nothing. No objects are in orbit around any star, no remnants of any formation process. Just the interstellar medium, atom by sparse atom, stretching across the remaining light years of the journey in perfect, featureless desolation. NASA confirmed this crossing in September 2013, based on detailed analysis of plasma oscillation data that indicated the electron density around Voyager 1 had increased by roughly a factor of 80 compared to conditions inside the heliosphere. The spacecraft had not just left the solar system's planetary region, it had left the solar system's entire protective envelope and entered a fundamentally different medium. Voyager 2 followed. Launched 16 days before its twin, but on a slower trajectory due to its detour past Uranus and Neptune, Voyager 2 crossed the heliopause on November 5, 2018. At a distance of approximately 119 astronomical units from the Sun, its crossing confirmed and expanded on Voyager 1's findings. Voyager 2 carried a working plasma science instrument that Voyager 1's had lost decades earlier, allowing it to make direct measurements of the interstellar plasma that its twin could not. The data showed that the interstellar plasma was colder and significantly denser than the plasma inside the heliosphere, exactly as models had predicted. Both spacecraft observed that the interstellar magnetic field was oriented in a direction parallel to the heliosphere boundary, a finding that surprised many scientists who had expected a sharper directional change. Since those crossings, the Voyagers have continued to send back data from interstellar space, and the findings have been consistently fascinating. In 2020, Voyager 1's magnetometer registered an abrupt increase in the intensity of the local interstellar magnetic field, accompanied by a rise in plasma density. Scientists initially interpreted these as pressure waves generated when bursts of solar activity slammed into the heliopause and sent reverberations rippling outward into the interstellar medium. But the anomaly did not fade. It persisted, leading some researchers to speculate that Voyager 1 might have entered a distinct region of interstellar space, perhaps a localized cloud of ancient plasma or a pressure structure not previously predicted by models. The investigation was interrupted in November 2023 when a hardware failure in Voyager 1's flight data subsystem caused the spacecraft to stop transmitting usable data. After months of painstaking remote troubleshooting across a signal delay of more than 22 hours each way, engineers traced the problem to a corrupted memory chip, likely damaged by a cosmic ray strike. By mid-2024, science data from multiple instruments had been restored, and the investigation of the interstellar anomaly resumed. These are extraordinary achievements of engineering and perseverance, and they reveal something profoundly humbling. As of early 2025, Voyager 1 is approximately 165 astronomical units from the Sun. That is roughly 24.7 billion kilometers. It is the most distant human-made object in existence, and it has been traveling for nearly 48 years. At its current velocity of 17 kilometers per second, it covers roughly 535 million kilometers per year. That sounds fast. It is fast by any standard of human experience. You could circle the Earth more than 13,000 times in a year at that speed. But Proxima Centauri is 4.24 light-years away. That is approximately 40 trillion kilometers. Voyager 1, after nearly half a century of continuous flight, has traveled less than 0.1% of that distance. If Voyager 1 were aimed directly at Proxima Centauri, which it is not, it would need over 70,000 years to arrive. 70,000 years. That is roughly 10 times longer than all of recorded human civilization. When Voyager 1 hypothetically arrived, the species that launched it might no longer exist. Voyager 2, slightly slower and slightly closer to the Sun, tells the same story. Both spacecraft are moving through interstellar space at speeds that dwarf anything humans experience in daily life, and both are barely crawling relative to the distances they would need to cover to reach even the nearest neighboring star. The interstellar medium they are now sampling, the thin plasma and the elevated cosmic ray flux, and the faint magnetic field, extends ahead of them for light years in every direction. They will spend thousands of centuries drifting through this medium before they come anywhere close to another stellar system. This is the first visceral lesson about the space between stars. It is not just empty, it is vast on a scale that makes human technology irrelevant. Our fastest machines, products of decades of engineering and billions of dollars of investment, enter interstellar space and are immediately rendered negligible by the sheer distance to the next destination. The interstellar medium does not need to block you or destroy you or push you back. It simply needs to exist at the scale it exists at. The emptiness itself is the obstacle. The distance itself is the wall. And the distance to Proxima Centauri is, cosmically speaking, trivially small. It represents the very shortest interstellar gap in our region of the galaxy. Most stars in the Milky Way are separated by far greater distances. Travel to a star 10 light-years away and you have multiplied the problem by more than 2. Travel to a star 100 light-years away, still a negligible distance within a galaxy that spans 100,000 light-years, and you have multiplied it by more than 20. The interstellar medium stretches across all of it, the same sparse atoms, the same near vacuum, the same cosmic silence. There is nothing between here and there that changes the equation. Just the medium, thin and featureless and unyielding, for trillions upon trillions of kilometers. Let us put the Voyager distance into one more frame to make the point inescapable. Imagine shrinking the solar system so that the sun is the size of a grain of sand, roughly 1 millimeter across. At this scale, the Earth would be a speck of dust orbiting about 10 centimeters away, roughly the width of your hand. Jupiter would be another tiny grain about half a meter out. Neptune, the outermost major planet, would sit about 3 meters from the Sun's grain. The entire solar system, from the Sun to Neptune, would fit comfortably inside a small room. At this same scale, Proxima Centauri would be another grain of sand sitting approximately 29 kilometers away. Nearly 30 kilometers of empty space between 2 grains of sand in a small room. Walk out of the room, through the hallway, out of the building, through the city, past the suburbs, and into the countryside for almost 30 kilometers before you reach the next grain. That is the distance between stars, scaled down to something you can hold in your hand, and everything between those 2 grains, every millimeter of those 29 kilometers, is the interstellar medium. Nearly empty, nearly featureless, just space stretching on and on and on. There is a reason this scale breaks human intuition. Our brains evolved to process distances measured in meters and kilometers. We developed spatial reasoning to navigate forests, track animals across savannas, and find our way back to shelter. Our cognitive architecture was built for a world where the farthest relevant distance was the horizon, maybe a few tens of kilometers on a clear day. Interstellar distances exceed our innate processing capacity by factors of trillions. We can write the numbers, we can perform the calculations, but we cannot feel them. The emotional reality of 40 trillion kilometers does not register in the same way that the emotional reality of a long walk home does. And so, we default to abstractions. We say 4 light years as though it were a comprehensible distance, when in truth it is a number so large it might as well be a magic spell. The words carry no experiential weight. This gap between what we can calculate and what we can feel is one of the reasons the space between stars is so routinely underestimated. Science fiction has trained us to imagine interstellar travel as a matter of better engines, faster ships, and more advanced technology. The stars are out there, and all we need is the right vehicle to reach them. What this framing ignores is the physical reality of what out there actually means. It means years of travel at the speed of light itself. It means tens of thousands of years at the fastest speeds any human technology has ever achieved. It means crossing a medium that contains, for all practical purposes, nothing useful, no fuel, no resources, no shelter, no landmarks. It means committing to a journey through a void so absolute that even the concept of progress becomes difficult to define. When the scenery does not change for millennia, when the nearest star is still light years away, when your instruments show the same sparse atoms and the same faint magnetic hum they showed a century ago, what does it mean to say you are getting closer? The density of the interstellar medium also means that there is effectively no way to harvest resources during such a journey. The concept of a Bussard ramjet, a hypothetical spacecraft that scoops up interstellar hydrogen and uses it as fusion fuel, has appeared in physics discussions and science fiction for decades. But the math is punishing. At 1 atom per cubic centimetre, a scoop hundreds of kilometres wide would collect only grams of hydrogen per second, even at high velocity. The drag created by the scoop interacting with the medium would likely exceed any thrust generated by fusing the collected fuel. The interstellar medium is simply too thin to serve as a resource. It exists, but it exists at densities so far below utility that its presence is almost taunting. There is something out there, just not nearly enough of anything. The Voyager spacecraft themselves are aging testaments to the harshness of this environment. Their radioisotope thermoelectric generators, which convert heat from decaying plutonium-238 into electricity, lose approximately 4 watts of power each year as the plutonium decays. By 2025, the power situation has grown critical enough that NASA has begun shutting down science instruments one by one to keep the remaining ones operational. In February 2025, Voyager 1's cosmic ray subsystem was powered off. In March 2025, Voyager 2's low-energy charged particle detector followed. These decisions extend the mission's life by a few years at most. Each spacecraft now operates with only 3 functioning science instruments. Engineers estimate that both Voyagers will exhaust their usable power sometime in the late 2020s or early 2030s, after which they will fall silent, drifting through interstellar space as inert artifacts, still carrying their golden records but no longer able to tell us anything about the medium through which they travel. When the Voyagers go quiet, humanity will have no active presence in interstellar space. No instrument measuring the density of the interstellar plasma, no magnetometer tracking the faint interstellar field, no cosmic ray detector is counting the high-energy particles that saturate the medium. We will be left with the data they collected and the knowledge that, just beyond the edge of our solar bubble, a vast and almost incomprehensibly empty environment stretches outward in every direction towards stars we cannot reach. This is the scale of what lies between the stars, not a gap, not a void to be leaped across with sufficient ambition, a medium so thin it barely registers as matter and so vast it swallows the fastest objects humanity has ever built without the slightest notice. The interstellar medium does not care about our spacecraft. It does not resist them. It simply extends, kilometre after kilometre, light year after light year, unchanging and indifferent, while our machines crawl through it at speeds the universe considers negligible. And yet the scale is only part of the story, because for all its staggering emptiness, for all its featureless expanse, the interstellar medium is not benign. The thin gas and the sparse dust and the faint magnetic fields are not simply obstacles of distance. They carry with them something more immediate and more dangerous than mere emptiness. The space between stars is flooded with energy. High-energy particles rain through it at nearly the speed of light, every second, from every direction. Radiation permeates it at levels that would be lethal to unprotected biological tissue over any sustained exposure. The medium that seems like nothing is, in fact, actively hostile, and that hostility only grows more severe the farther you travel from the one thing that has been protecting you all along. Every second of every day, something invisible passes through your body. Not one thing, hundreds of things. Subatomic particles traveling at nearly the speed of light, remnants of catastrophic stellar explosions that occurred thousands or even millions of years ago, cross through the walls of your house, through the roof above you, through the ground beneath you, and through every cell in your body without stopping. You do not feel them, you cannot see them, they leave no trace that your senses can detect. And yet they are there, a constant rain of high-energy radiation falling from space. On the surface of the Earth, this is a minor footnote in your daily life. The planet's magnetic field deflects the majority of incoming charged particles, sweeping them into spiraling paths that funnel toward the poles rather than allowing them to strike the surface directly. The atmosphere above you, a column of gas hundreds of kilometers deep and pressing down with the weight of an ocean, absorbs most of whatever makes it past the magnetic shield. By the time cosmic radiation reaches sea level, it has been filtered, scattered, and attenuated to levels so low that the average person receives roughly 0.3 millisieverts per year from cosmic sources, a small fraction of the total background radiation exposure from all natural and medical causes combined. You live at the bottom of a double shield, magnetic and atmospheric, and that shield is so effective that most people go their entire lives without ever learning it exists. In interstellar space, both shields are gone. The heliosphere, that great bubble of solar wind plasma that the sun inflates around the entire solar system, acts as a third layer of protection that most people never think about. The solar wind, a constant outflow of charged particles streaming from the sun at 400 to 800 kilometers per second, pushes outward against the surrounding interstellar medium, creating a cavity roughly 120 astronomical units in radius. Within this cavity, the sun's magnetic field extends outward in a vast spiral, and the pressure of the solar wind keeps a portion of the incoming galactic cosmic rays at bay. The heliosphere does not block all cosmic rays. Higher energy particles punch through regardless, but it significantly reduces the total flux of galactic cosmic radiation reaching the inner solar system. Measurements from neutron monitors on Earth show that cosmic ray intensity at the surface varies with the 11-year solar activity cycle. During solar maximum, when the solar wind is strongest and the heliosphere is most inflated, cosmic ray flux drops. During solar minimum, when the wind weakens, more cosmic rays penetrate. The heliosphere is a dynamic shield, constantly breathing in and out, and everything inside it benefits from its presence. We already know what happens when you leave that shield behind. Voyager's instruments confirmed it directly. The galactic cosmic ray flux in the local interstellar medium is significantly higher than the flux inside the heliosphere. This was expected on theoretical grounds, but the Voyager crossings turned prediction into measured fact.